Hi, good morning everyone. This is K. Narsimurthy and I work in Government First Aid Women's College, Tumkur. I am going to present my 19th video for the second semester BSc students of Tumkur University, and the subject which I am presenting is physics. So almost we are in the second unit now. First unit is over. The first unit consists of 15 hours or 15 sessions, and that is over. In the second unit, this is my this is my fourth video in this second unit. 3 videos I have presented in this unit. In these 3 videos I discussed about the magnetostatics. In the magnetostatics, very basic phenomena is magnetic effect of electric current. That was discovered by Astad, and the name itself indicates that when a current is passed through a conductor, it produces a magnetic field around it, and this phenomena is known as magnetic effect of electric current. Right. So this magnetic field produced, the direction of the magnetic field which is produced is given by the right hand thumb rule, and which I explained in detail in my 16th video. And the magnitude of the magnetic field which is produced around the conductor is given by the Biot-Savart's law. So Biot-Savart's law gives us the magnetic field dB, which is equal to mu naught by 4 pi IDL sine theta divided by r square. That is the magnitude of magnetic field which is produced around the current carrying conductor. Okay, so we got the direction from the right hand thumb rule, and we got the equation for the magnitude of magnetic field which is produced from the Biot-Savart's law. We got a complete thing. After that, I applied same Biot-Savart's law for different situations, and I found the magnetic field equation for magnetic field. The first case which I discussed was the magnetic field due to a straight conductor carrying current, and also magnetic field due to a circular coil, and the magnetic field due to a solenoid. These are the 3 different cases which I discussed in my previous 2 videos. Now in this video I am discussing one more case. I am applying Biot-Savart's law once again, and let's see what I am going to discuss here. Right. So before discussing the cases, let me know some more things about the magnetic field. Let me know about the divergence of magnetic field. See, the magnetic monopoles does not exist. We can have magnetic dipoles. So magnetic poles will coexist. You can expect only the 2 poles at a time. You cannot expect a single pole to be exist. You cannot expect a monopole to be exist in the magnetic field. Okay, so you cannot expect only the north pole, or you cannot expect only the south pole. They exist together. So magnetic monopoles cannot exist. Only we can expect magnetic dipoles. Okay, this implies that there cannot be any divergence of the magnetic field. So therefore the divergence of the magnetic field is 0. So magnetic lines of forces cannot diverge out from a point, because there is no monopole here. You cannot expect a magnetic lines to come out from a point, or you cannot expect a magnetic lines to converge to a point. Therefore 2 things are not possible in this case, because magnetic field is a rotational field. So you cannot expect any divergence of magnetic field, and that is 0. This is a kind of Gauss law, you can say, in the magnetism. We know what is Gauss law in the electrostatics. So this is a kind of a Gauss law in the magnetism. According to this law, you can say that magnetic monopoles do not exist, because the divergence of this magnetic field is going to be 0. Right. Let us see, can we have some integral of magnetic field with some area dA? Can we have a magnetic lines of forces coming out of an in infinitesimally small area dA. If I look into that, the integral of B dot dA is also 0. This above equation represents the net flux which is coming out of the surface. Again, that is also 0. You cannot expect a flux lines coming out of a surface area. Means you cannot have a divergence of this. So lines, magnetic lines of forces cannot crash these area normally. Okay, because it is a rotational field, you can only expect a lines of forces which are you can have a rotational field. You cannot expect a lines which is coming out of an area. So line integral of B dot dA is also 0. Yeah. Curl of a magnetic field, you can expect a non-zero value for a curl of a magnetic field. As I've been telling you that the B is a rotational field. Magnetic field is a rotational field, whereas the electric field is an irrotational field. Therefore, you can expect a divergence of electric field to be non-zero, but you cannot expect a divergence of magnetic field to be non-zero, but you can have a curl of a magnetic field to be non-zero, and this curl of a magnetic field which is equal to mu naught times the current density. So curl B is equal to mu naught times the J. J is called current density, which is current flowing per unit area. Right. We have a very interesting law in this magnetostatics, which is called Ampere's circuital law. Just like how discussed the Gauss law in electrostatic, we have some more laws in the magnetostatics. The one law which I am going to deal now is the Ampere's circuital law. So it states that the line integral of magnetic field over a closed path. Be careful, it has to be a closed path. So line integral of a magnetic field over a closed path is equal to mu naught times the total current enclosed in that closed path. Okay, so Ampere circuitize, it's analogous to Gauss law in the electrostatics. How I am considering a Gaussian surface, how I am looking for the flux which is coming out of the surface, how I am equating that to a 1 over epsilon naught times the total charge enclosed. Exactly in the similar way, I am looking for the magnetic field, magnetic lines of forces which is coming out of this small this thing dl, and that is equal to mu naught time. It is line integral of magnetic field over a closed path is equal to the mu naught times the total current enclosed in that loop. So you need to consider a closed path, and you can apply the Ampere circuital law very easily for that closed path. Just like how I considered a Gaussian surface in electrostatic, here to apply an Ampere circuital law, you need to consider an imaginary closed path and look for the magnetic lines of forces, magnetic field over a closed path, and you can equate that to the mu naught times the current enclosed in that closed path. Alright. Now I am defining the terms involved in that Ampere circuital law equation, and that is B is the strength of magnetic field and dl is an infinitesimally small line element on the closed path, and you know what is the mu naught is. It's a permeability of free space. As I told you, the permeability is a capacity of a medium which allow the magnetic lines of forces to pass through it. If it allows more and more lines of magnetic lines to pass through it, its permeability will be more. If it allows less magnetic lines to pass through it, its permeability will be obviously less. Yeah, I is the net current enclosed in that closed path. You have to be little careful while defining the I here. I is the net current enclosed in the closed path, not in anywhere else. It is pertaining to the closed path. Yeah. Now I will discuss a little proof, very small proof of this Ampere circuital law. Now I am going to prove this Ampere circuital law in a very simple manner. So I need to prove that line integral of B dot dl is equal to mu naught times the current. Mu naught times the current enclosed in the closed path. Right, for that I am considering a straight conductor which carries a current. It is a straight conductor, it's a circular conductor, and it is carrying the current I. So if I apply Biot-Savart's law for this, according to Biot-Savart's law, the magnetic field due to a straight conductor at some distance r is equal to mu naught I divided by 2 pi r. This is the equation which I derived in my previous video. Magnetic field due to a straight conductor which is equal to mu naught I divided by 2 pi r. The same equation which I derived, I am using it to prove the Ampere circuital law. Yeah, I have proved this using Biot-Savart's law. Alright. Now this is a circular conductor which I am imagining. Okay. Now I am looking for the magnetic field at some point P, which is at a distance of r from this small length dl. So if I look at the magnetic field at that point dl at some small length dl, the B will be tangential to the circle of radius r, and B is a constant at all points on the circles and is parallel to the element dl. Okay, so this is the conductor which I am considering. It's a circular conductor. The conductor is a straight conductor. I'm sorry. Conductor is a straight conductor. It is not a circular conductor. You please make the correction here. It is a straight conductor. Look at the diagram. It's a straight conductor. Okay. So in that straight conductor, there is one circle I have drawn. This is the closed path I have drawn. Okay, I'm sorry, it is not a circular conductor. It is a straight conductor. I have drawn a circular path around the conductor. Okay, so in that circular path I am considering a small length dl where the magnetic field is tangential to that. Okay, the circle which I have drawn is of radius capital R. Now I can apply I'll find out the line integral of B dot dl. Okay, so this line integral of B dot dl is equal to B line integral of dl, because B will not apply to the integral because B is same, magnetic field is same all around the circular closed path. Now what is dl? dl, you have to, one small portion I have taken in a circular path. If I take one full circular path, it is exactly the circumference of the circle. Circumference of the circle is 2 pi r. One round in a circle will give you the circumference. So complete one round is the circumference. It is 2 pi r. So B into 2 pi r. Now that's what I have told you. That's the circumference of the circle. Now I can substitute in the previous equation. So line integral of B dot dl is equal to mu naught I divided by 2 pi r. So this is the equation for magnetic field which I have derived in my previous video using Biot-Savart's law. That equation I am using in here, mu naught I divided by 2 pi r into this 2 pi r. Where comes this 2 pi r? This 2 pi r is the circumference of the imaginary path, circumference of the closed path which I have considered. Okay, it is of radius r. Okay, 2 pi will get cancels. I left with a mu naught I. R will also get cancels. I left with a mu naught I. And there I derived the Ampere circuital law very easily by considering a straight conductor. Okay, so this is a very simple proof of the Ampere circuital law. This I derived by considering a straight conductor and by knowing the magnetic field at some point P at a distance of r from the conductor, and that equation is mu naught I by 2 pi r, which I have derived in my previous video using Biot-Savart's law. Yeah, let me move further. and let us derive an equation for magnetic field at a point on the axis using Ampere circuit law. Students, I have derived an equation for magnetic field using solenoid by applying the another law, which is Biot-Savart's law. We did it using Biot-Savart's law. Now we are trying to do that same thing using Ampere circuit law. Let us see, do I get a same equation what I get in my previous video, what I derived by using Biot-Savart's law. Do I get the same thing or not? We'll see this. Okay. Now you know what is solenoid is. It is a circle. It's a coil which is wound in the form of a cylinder. The coil wound in the form of a cylinder, and current is flowing in the solenoid. Let I be the current which is flowing in the solenoid. It produces a magnetic field. Okay. These magnetic lines of forces are parallel to the axis of the solenoid. So we have a solenoid, current flowing through it, and it produces a magnetic field, and lines of forces are parallel to the axis of the solenoid. Fine. Now where I am finding the magnetic field here is, I am going to find the magnetic field at point P. Look at the diagram, I am mentioning the point P there. Now exactly at that point P, I am going to draw a closed path. This time my closed path is a rectangle. Now you can draw any shape you want, but it has to be easy for calculation. So for my calculation, I am drawing a rectangular surface which will be very easy for me to calculate the line integral of B dot dl. Okay, so this time I am drawing a rectangular surface of ABCD. And length of this is L, which is clearly mentioned in the diagram. Yes. Now I have to apply the Ampere circuit law, and I have drawn the rectangular loop ABCD which is passing through the point P. The magnetic field is uniform, as I know, and is parallel to the length of the solenoid. These are the two things which I know already. The magnetic field is uniform inside the solenoid, and it is parallel to the axis of the solenoid. Of course, it is parallel to the length of the solenoid as well. Now, so let N be the number of turns per unit length of the solenoid, which I have defined in my previous video itself. The N is number of turns per unit length. Now, number of turns in that small length of rectangle, capital L. In that small length, what could be the number of turns? Number of turns will be simply N into L. N is number of turns per unit length multiplied by capital L will gives you the number of turns in that L, that rectangle of length L. Okay, it is simply how I calculate the 1 kg sugar is 40 rupees, and what will be the value of 5 kg sugar. So for 5 kg sugar, it is simply 40 into 5. So exactly in the similar way I can do it here also. For unit length we have N number of turns. For length L, it is N into L. Yeah. Total current passing through the loop ABCD will be equal to, now it is not just I, the current in that loop. I have told you it is current enclosed, it is a net current enclosed. You cannot take simply I here for current. You have to calculate the net current enclosed in that closed path, and this net current enclosed will be the number of turns into the current. The number of turns in that rectangle will be N into L, and the current is N into L into I is the net current enclosed in that closed path, in that rectangular closed path. Right. Now I will apply Ampere circuit law. I'll take the Ampere circuit law as it is. It is line integral of B dot dl is equal to mu naught I. Now what is I? I just calculated the current enclosed in the closed path is mu naught L into I. Because for I am substituting NLI. No, don't get confused with this I and this I. Either you make it small letter I in the formula in the Ampere circuit law, and after that you make it NLI. Okay, Right. So it is mu naught n L I. Right. I need to calculate the left hand side of the Ampere circuit law, which is line integral of B dot dl. So now I have to take one complete path in this rectangle of ABCD. So I have to consider each side. We have four sides in the rectangle: AB, BC, CD and DA. I have to go one round in the rectangle. First I will go from A to B. So line integral of B dot dl is line integral A to B B dot dl plus I will go from B to C, take line integral B to C B dot dl. Then I will go from C to D, line integral of C to D B dot dl. Then I will come from A to B. You can look with the diagram and also you can say that. Yeah. First I am going from A to B, and then from B to C, and then C to D, and then from D to A. So one complete path I'm splitting a line integral over this closed path into four parts. One is from A to B, B to C, C to D and D to A. Okay. This line integral has been split into four parts. Now first let me take the first part and see what it is. A to B, line integral from A to B. Okay. So B dot dl, it's a dot product. I can say it is B into dl into cos theta. You know what cos theta is? Cos theta is the angle between the magnetic field and the length dl. Okay. So this time magnetic field, like I have told you that it is parallel to the axis, it is parallel to the length. Okay. So your length AB is again parallel to the magnetic field. So therefore the theta is 0. So this time theta is 0. It is line integral of B dot dl because cos 0 is 1. No. Yeah. A to B B dot dl. B I can take out of the integral because magnetic field is same inside the solenoid. So A to B dl. Yeah. Integral of A to B dl is what we need to calculate now. It is simply the length of the solenoid, length of the rectangle. It is simply the length of the rectangle which I imagined. Okay. So therefore it is B into dl. Right. Still I need to calculate the three integrals. One is from B to C, C to D, another is D to A. Okay. Now I'll take these two integrals and I will analyze this. B to C and D to A. Here B and dl are perpendicular to each other. Magnetic field and the length are perpendicular to each other. You can go back and see. For these two cases, look at BC and look at DA. For these two cases, the magnetic field is along the axis and this two lengths, one is BC, another one is DA. Both these length are perpendicular to the magnetic field. You observe this diagram carefully. This B magnetic field and the length BC and AD both are perpendicular to the magnetic field where theta is 90. Theta is 90 for these two cases. So cos 90 is 0. Therefore you will get line integral B dot dl as 0 for these two cases. One is from B to C, another is from D to A. It is from D to A, okay? For D to A it is 0. But for C to D, I'll go back and I'll analyze this. Look at C to D. C to D is outside the solenoid. The line, the rectangle, the line which I have considered, the path which I have considered, C to D, is outside the solenoid. Therefore, outside the solenoid, the magnetic field is 0. We know this fact that the magnetic field outside the solenoid is 0. Okay, so magnetic field along this BC is also 0, along this DA is also 0 because BC and DA are perpendicular to the magnetic field. So you can only expect a magnetic field along this length AB. All three sides becomes 0, their contribution is 0, So we can only have a contribution from AB path. So AB path is just B into L, length of the rectangle. So all these three become 0. 2 becomes 0 because they are perpendicular to the magnetic field. Another one is 0 because it is outside the solenoid. So outside you cannot expect a magnetic field. Right. So overall, I can say that line integral of B dot dl ABCD is equal to, it is simply line integral of A to B dot dl, which is equal to B into L. Okay. So now I can take this the law, Ampere circuit law. Okay, line integral of B dot dl is, I have calculated, it's B into L. B into L is equal to mu naught I. Mu naught I is mu naught NLI. Mu naught NLI is equal to B into L. So LL get cancels and B is equal to mu naught NI. So comparing the equation 1 and 3, I got the magnetic field as mu naught NI. So in my previous video, by using Biot-Savart's law also, I have calculated the magnetic field due to the solenoid. I got exactly the same equation. So either you use any law for that matter, you use Biot-Savart's law or you use Ampere circuit law, the magnetic field of a solenoid along the axis will be the same. I am getting mu naught Ni this time, and there also I got mu naught Ni. So any law you use for that matter, magnetic field due to a solenoid will be the same. I got the same equation this time also. These are some of the books which I have referred. Students, you please go through these books. You will understand these Ampere circuit law and the application of this to a solenoid to find the magnetic field along the axis. These things are available in these books. You please go through this. You will understand the things better. So thank you very much.